Okay, so I am going to go over how I do power problems, and I don't use all of those formulas because I find all of those formulas, it's like you're saying, it's too kind of overwhelming. It's like, well, do I use this one or do I use that one? I just kind of stick with the basics, and then from there, I can figure stuff out. So there are some things that I know. I know, and this one is not going to change, that V equals I times Z. That's Ohm's law, and I'll use that one, and I'll use that one with the complex numbers to get complex voltage and complex current and all of that. I also know that power, I learned in circuits 1 that power equals VI. Well, that is true when you're in DC. So now that we're in AC, we have complex power. And I'm putting a little squiggle on top of it to show that I'm talking about the complex power that has a real part and has an imaginary part. And the complex power equals the complex root mean square voltage times the complex root mean square current conjugate. Okay, so the reason that you sometimes have a 1/2 and sometimes don't have a 1/2 is if they give you peak, then you put a 1/2 in, because V RMS equals V max over the square root of 2. And I RMS equals I max over the square root of 2. And so if I multiplied these two together, I would get that 1/2. So these two things you do need to know. So that it's V times I conjugate, and that you have a 1/2 if it's not RMS, and if it's RMS, you don't have a 1/2.
V max equals to V and I max equals to I?
Usually, yes. So like if you have something like this, if this is given to you as V equals 20 angle 30 degrees, that means 20 cosine omega t plus 30 degrees. This 20 is your amplitude, it's your max.
Oh.
So when you're given a phasor, it is usually the max unless it specifically says RMS.
Okay.
So if they just give it to you like this, then VRMS is 20 over square root of 2.
Okay, that's perfect.
Okay, so the other thing that is true is that your complex power equals your real power plus J times your reactive power. So P is real power. It's also average power. And it's what you get from resistors. Or it's when you're looking at your circuit, if you're trying to figure out which ones are consuming, resistors, consume real power.
And that's the same formula as for the DC one, P equals to VI?
We're not going to use that though.
Okay, we're not.
Okay, yeah. And then Q is the reactive power. And that's going to be your inductors and capacitors. And it's negative for capacitors and positive for inductors. Notice Q itself doesn't have a J in it. The J is up here. Okay, so these are my steps. So the way I do it is I use complex values for everything. When possible, I use S equals 1/2 VI conjugate. That's almost always possible, and it is always correct. I mean, the 1/2 might not be, I mean, you might make a mistake somewhere, it might not need the 1/2, but you can always use it.
Would you say the basics you taught us is you can solve any complex power, what our professor can test us on based on those basics?
Mm-hmm.
Okay.
It's how I did it is when I took it. So, for instance, let me just get a problem, and I'll show you how to make it work. And so using that and using Ohm's law, you can pretty much get, okay, you'll also have to deal with the power factor. So what is the power factor? The power factor, the way I think of the power factor is this angle here. The power factor is the cosine of theta, and I just, the way I remember it is just with this triangle, because I know that the real part is the horizontal part, the reactive part is the vertical part, and the cosine of this angle is the power factor.
That S is the magnitude of the complex power?
Yes, it is.
Okay.
Yep. And that has a name, so the magnitude of the complex power is called the apparent power. Okay, so the one time I do use the formulas is for figuring out the shunt capacitor, because it's a lot easier for the shunt capacitor just to use the formulas that he gives you. So let's look at a problem with this. And I'm just going to pick any problem.
And have you seen how his exams looks like?
Mm-hmm. Yes, I'll pick a problem like something I think he would put on an exam. Okay, so let's say I have So I've got a circuit. And I have I s of t is 20 cosine 10 to the third t plus 30 degrees milliamps. Rs is 400 ohms. R1 is 200 ohms. R2 is 2 kiloohms. C is 1 microfarad. And I want to determine I V S P average and Q for load to the right of AB, and I also want to determine the apparent power for the capacitor and the apparent power for the current source. So these were apparent power. These were all complex. Okay, so the first thing that I need to do is get everything into the phasor domain because it wasn't already given to me as phasors. So my current is 20 angle 30 degrees. That's IS, that's my current source. My capacitor is going to be, so Z of the capacitor will be minus J over omega C. What is omega?
Isn't it frequency times 2 pi?
It is if you were given the frequency, but we weren't given the frequency.
Okay.
So what you said was not wrong, but it doesn't help us here.
Okay.
It's either 20 or 10 to the third.
Yes, it is. I've already used the 20,
That's the 10 to the third.
so it's 10 to the third. Yeah, it's the number in front of the t. So omega is 10 to the third. So F, so omega equals 2 pi f. And so if they give it to you in hertz, so if they say, so this is kind of an aside, this is not for this problem. If they say the frequency is 60 hertz, then omega is 2 pi times 60, which I think is 377, something like that. But if they give it to you as an equation, it's this number right here in front of the t.
Does it matter whether they gave us like the voltage ST equals to, like, does it matter if we're given the voltage of the current, whatever the numbers in front of T is also the omega?
No, it does not affect the phase, but I do see something that it does affect that I missed. This was milliamps, this was 0.02. It's milliamps?
Yeah, no, that's what I'm.
Oh, yeah. So no, it does not affect, the only thing it affects is coming up with the phasors.
Okay.
So it does not affect the voltage or the current.
No, I'm asking if we were given the voltage T and they told us, instead of IST basically, it's VST. Does that matter?
No, it works exactly the same way. Yeah. Okay, so ZC is minus J over omega, which is 1,000 times C, which is 1 microfarad, so that's 1 times 10 to the negative 6. So it's minus J over 10 to the minus 3, which is minus J 1,000. Okay, so now I want to think about this the same way that I would have thought about this in circuits 1. I want to figure out, I want to figure out the power, because that's what it's asking me. And so I want to figure out, if possible, V and I, but in order to do that, I'm going to have to get the impedance of everything that's going to count on the load. So if I look at the load right here,
Oh,
that's the load, because it said everything to the right of A and B.
oh, okay.
So I don't have a worksheet. Yeah, I just picked a problem to do, because I looked through my old worksheets and they just, I didn't like them. They were messy and I didn't have time to make a new one, and so I figured I could just do some problems. Figured that nobody would mind. All right, so my impedance of my load is R1 plus R2 in parallel with C. So that is going to be 200 plus 2,000 times minus J 1,000 over 2,000 minus J 1,000. And at this point, he's not going to ask you to show your work for doing complex arithmetic, so don't. I mean, do if you want to, but I do much better with using the calculator than trying to do it by hand.
It wastes too much time.
It wastes a lot of time when you can get it easier. So I want 200 plus 2,000 times minus J 1,000 over 2,000 minus J 1,000, and I get 1,000 angle negative 53.1. Let me see what that is in rectangular. Oh, that's pretty. 600 minus J 800I.
Oh, wow.
I mean, just minus J 800 ohms. Okay, so how am I going to use that? I can use that both in current division and in voltage division to get my V and my I. So for my current division, if y'all recall, the way that I do current division is if I have this is I, and this is Z1, and this is Z2, and this is I1, and this is I2. I1 equals I times Z2 over Z1 plus Z2. Now, y'all had learned a formula in Circuits 1 involving R equivalent. It is the same thing as this, it just has more stuff in it and more places to make mistakes. So I1 is I times Z2 over Z1 plus Z2, and I2 is I times Z1 over Z1 plus Z2. So if I want to get the current through the load, so I now have the current is coming this way, and it can go through RS or it could go this way. So the current through the load will equal my total current. Now, right now I'm still, no, this was 0.02. I'm keeping in mind that this is not RMS. It doesn't matter yet. It will matter when I go to do the power. So this will be 0.02 times 400 over 400 plus 600 minus J 800.
You multiply it by 0.02. Well, isn't I that formula you gave us?
I is just this current right here.
Yeah, you said it's 20. Oh, I'm sorry, I can't read.
It was milliamps, so that's why it became
Yeah.
that. Yeah. Oh, except I did forget the angle 30. Yeah.
So you have to convert it to rectangular form.
No, you don't have to. You can use whatever form you want. So I will do,
Oh wow, this is all.
yeah, 0.02. Yeah, I don't have to convert. Angle 30 times, and then my fraction was 400 over, I think I can do this in my head without making a mistake, but this is where I mess up. 400 plus 600 is 1,000. 1,000 minus J 800, and I get 0.006 angle 0.00625 angle 68.66, or in rectangular, I just get both just in case I need it for something. 0.00227
Really small radians.
plus J 0.005818. All right. Remind me when I finish this problem, I have to text somebody. So I know y'all are all very concerned about my texting. All right. Okay, so now I got the current through the load. In order to get the power, it's easiest for me to have the current and the voltage through the load. I think the easiest way for me to get the voltage through the load is just to use Ohm's law, because I have the impedance. So I could do voltage division, but to do voltage division I'd have to do a source transformation and then do voltage division. But I have the impedance right here and I have the current, so it's easy enough to just say V for the load will equal 600 minus J 800 times 0.00227 plus J005818. So on the calculator, I'm going to take my second answer. So I'll take my answer from my last problem times, and I need to be careful to use parentheses, 600 minus J 800. And I get 6.247 angle 15.53, and in rectangular, just in case I want it, .019 plus J 1.673 volts. Okay, so now I know my complex power for the load is, now I remember that, okay, this was not RMS, so I need a 1/2. V 6.247 angle 15.53 times I conjugate. So to make the conjugate, if I'm using the phasor form, I make the angle negative, or I change the sign of the angle. And if I'm using the rectangular form, I change the sign of the imaginary part. Basically, you're changing the sign of the second part of the number. Does anyone remember if this was 6.6 or 6.0?
6.
6.6. So I'm going to get careful to use parentheses. So this was my voltage times, and I'll get my current. I think this was my current. And I'm going to change the sign of the imaginary part.
Would you say each time we're giving a circuit, we can safely assume it's got to be a sinusoid graph if it's a DC circuit?
Well,
Oh,
not
I
a,
mean AC. I'm sorry.
yeah,
That's it. Okay, that's why we're able to take advantage that VRMS, for example, equals to amplitude of V divided by square root of
exactly.
2. Okay, just making sure.
Okay, so I get let's see, not the right answer, why not? I have the right I. I have the right V. I forgot my 1/2. Times 0.5. And now I have the right answer. Okay, so in phasor form, 0.019 angle negative 53.1. And what are my units for this? VA, volt amps. And then in rectangular form, it is .0117 minus J .0156 VA. So once I have that, once I have all this, I have all of my answers. I have, here is my complex power. It's 0.019 angle negative 53.1 VA. Here is my apparent power. It's 0.019 VA. It's just the magnitude. My real power is 0.0117 watts, and my reactive power is negative 0.0156 volt amps reactive.
Okay. So, what I'm also confused about is that we talked about finding, whenever you're finding power in AC, is that the same thing as finding complex power, or is there a difference between complex power and finding power in D?
These are all power.
Okay, these are,
So my answer to your question is, I always find complex power, and then I answer whatever question they're asking me.
okay, and would you say finding a power in an inductor and capacitor is the same thing as saying finding the complex power?
Kind of. So that's going to be the next part of this problem.
Oh.
Okay, so the next part of the problem said, so that was to find the power for the load. The load had resistors and capacitors, so it had complex power. He's very sleepy. Yeah. So, but it also asked us, the problem also asked us to find the power for the capacitor and the power for the current source. Now the capacitor is only going to have reactive power. Capacitors and inductors only have reactive power, and resistors only have real power. But you don't need to know that to work the problem. You just need to do the same thing you've been doing all along. But if I wanted to, it's actually very easy at this point to say what the power for the capacitor is, because if you look at the load, look at what the load is made of.
Resistors and capacitors.
Well, and how many capacitors?
One.
Just one. And so all of the imaginary part has to be due to the capacitor. So I don't really have to do any more work for this. I can say that the apparent power for the capacitor is minus 0.156 var.
Okay, that makes sense.
The current source is going to be a little different though. The current source it's because it asks for the power for the current source.
Oh, okay.
So the current source is going to be a little bit different. So could we say that the voltage for the current source is the same as the voltage we found for the load?
No, because there's a RS over there. So you would need to make it in parallel. You would need to make the load, the impedance of the load parallel with RS, and then that would be the same voltage.
The load is in parallel.
Oh, but it's not parallel with the other RS in the left.
Sure it is.
Oh wait. Oh yeah, you're right. Oh, they're all in parallel.
Yeah,
All would have voltage.
sure, because we found the equivalent impedance. So we had our current source, and we had RS,
Oh.
and we had our Z load.
Yeah, that makes sense.
So they all have the same voltage.
Yes, I agree.
So our voltage for our current source is 6.247 angle 15.53. The current for our current source, it's a current source, so we know what it is. It's 0.02 angle 30. So our complex power will be 6.247 angle 15.53 times 0.02 angle negative 30. Times 1/2.
Yeah. Well, when isn't it supposed to be its amplitude?
Yes?
Um.
I'm showing you the way I work it.
Okay.
So I always just find the complex power and then I answer the question they ask me. Because when I find the complex power, I also find the amplitude. I can use all those other formulas if I want to, but that's just a whole bunch of other formulas when I only need the one. So I already have everything I need, so it's not, it might theoretically be easier some other way, but
No, I agree with you, but
I like my way.
I agree with you, but the formula for that one is a half times the amplitude Vm times the amplitude of I. Isn't the amplitude like, so if it's the amplitude, why does it have angles?
I haven't finished yet.
Oh.
So what does amplitude of a complex number mean anyway?
What's it mean? Isn't it like the highest, like its peak?
The amplitude of a complex number is the square root of the real part squared plus the imaginary part squared. And so the amplitude depends on both the real part and the imaginary part. Now, there's ways to just use amplitudes without using the real part and the imaginary part, but it's all in there. And so uh, so it's not, it's not.
Yeah, okay, I get
I
it.
think you're confusing amplitude of a complex number with amplitude of a sinusoid, which they're related here because it is phasors, but, yeah. So, and then once I multiply them, my amplitude is right there. It's the magnitude of the phasor, 0.06247.
Oh, okay.
So my complex power is 0.06247, angle negative 14.47, VA, but they just asked for my apparent power, which is 0.06247.
Okay.
And I don't find it any easier to find this power by using any of the other formulas than just using this one.
Would you mind scrolling up a little bit then?
Yeah,
Yeah. No.
yeah, I'd mind.
Oh.
Where do you want to go?
No, I just wanted to you see how when I'm in go a little bit up whenever you up a little bit. Oh, you also did it there. Never mind. I'm sorry.
I do it I always use the complex values.
Yep.
I always use the complex values, and again, that's just me, and I know that a lot of people don't, because, the complex values, it's like, well, what does that part even mean? The apparent power versus the real average power, but I find it easier just to do it this way, and then just pick out the parts that I need.
Okay.
All right. Everybody had fun? Ready for a Bodie plot? Okay.
What's that? Oh.
Ooh.